Welcome everybody. In this video I want to tell you a little bit about the story of this axiom of determinacy, which I feel is a pretty cool axiom and has some interesting consequences. So let's take a look about this determinacy axiom is for the determinacy of infinite games. So this axiom that we're going to be talking about, which we're going to denote full determinacy, is going to refer to the following statement. In every infinite game, one of the two players has a winning strategy. Okay, so I'm going to explain that in more detail what that means in a few slides. But that's what the kind of statement we're talking about. Every infinite game, one of the two players has a winning strategy. And what kind of games we're referring to? Well, they have to be two-player games of perfect information, countably infinite and not more. There are a few things you have to specify to make this clear. But let's not get into the details for now. Okay, so what's up with this statement? It's pretty elegant, as we're going to see. It has very nice consequences. We're going to see some of the consequences, and they're pretty nice. And you would say it makes the world a better place, the set theory world a better place. So it's great, but it has one slight problem. It's false. So full determinacy is just plain false. What does it mean to be false in the world of set theory? It's not that clear what it means. So let's see what we mean here by false. It contradicts the axiom of choice. That's the problem with it. So let's take a look at this a bit better. So actually, without assuming the axiom of choice, we wouldn't show that full determinacy is consistent. So it causes no trouble with the rest of the axioms of CFC. This is assuming some hypotheses that are beyond CFC, let's say. But well, morally, this is what the theorem says, that it should be consistent unless for the axiom of choice. So without the axiom of choice, it might be okay to use it. Though the axiom of choice is a quite important axiom. Okay, so let's see what the axiom of choice says. So full determinacy is what we have up there, the same thing we mentioned before. The axiom of choice it contradicts full determinacy, as we mentioned before. That was proved by Gale and Stewart in the same paper where they introduced full determinacy. They showed that it contradicts the axiom of choice. So they show it, and it's not that good. So the axiom of choice, as we've been seeing so far in other videos, it says that you have a non-empty collection of disjoint sets. You can pick one element from each set. Okay, so like here you have all these sets. You can pick just one. It's a function that picks one from each. Of course, for finite sets, this is trivial. It's interesting when you have like large continuum size sets, let's say, or infinite sets, and you have to pick one from each. As a human, you couldn't just go and pick one from each randomly. You need something to pick them from you. And that's what the axiom of choice does, just picks one element from each in a non-constructive way. If you had a way of constructively say how to pick each element, then you don't need the axiom of choice because you're actually explicitly saying, building your set. The axiom of choice is useful when you don't know how to choose them in a concrete way, and you need magically somebody to choose the elements from you. So let's consider a weaker version of choice that actually works, which is called countable choice. And countable choice is the same as the axiom of choice, but the collection of sets that you're taking elements from is assumed to be countable. Okay, so that's a weaker version of the axiom of choice. In that one, you have a countable collection of sets. You're picking one from each. You can imagine more than how you would do that. Well, I mean, I don't know what do means here, but you're just picking one from each. It's a countable collection. Well, if you have like continuum size class of sets, picking one from each, you couldn't even go in order to pick them. I don't even know how you pick them. So Witten's theorem actually is a bit stronger and says that full determinacy is consistent not only with CF, Zermelo-Fraenkel without choice, actually it's consistent with Zermelo-Fraenkel and choice only for the countable set. So it's consistent with countable choice. Again, assuming these large cardinal assumptions. So the problem is when you do have a larger choice to make. Okay, so full determinacy and axiom of choice don't play along well. Why do you say that determinacy was so good? Let's see how what are the conclusions that we get from them, like some examples of conclusions we get from them. So a very famous result called the Banachitarsky Paradox, it's not a paradox, it's actually a theorem, that you can prove from the axiom of choice, is that you can break the three-dimensional unit ball. So imagine this is like a three-dimensional unit ball, like with everything that it has inside. You can break it up into finitely many pieces, which you can rearrange by translations and rotations, but without making them bigger or smaller. So you just move them apart, translations, rotations, put them back together, and you can build two balls also of the same radius, of radius 1, the same as you started with a ball of radius 1, and then you might make two balls also of radius 1. So the same, these new two balls look exactly the same as the original one, but now you have two instead of one. And what you did was break into finitely many pieces, put them all together in the right way, and now you get two balls. You will say, something is odd here, you shouldn't be able to do that. Well, the axiom of choice lets you do that. One reason is that these pieces are not measurable. They couldn't have a measure. If you had a measure, the sum of the measures should be the volume of the ball, and you couldn't like double the size. So you break it in non-measurable sets in this very smart way using the axiom of choice, and you manage to build two. And actually, you can build two, you can build three, you can build as many as you want just from one ball. So that is a strange theorem. That's why it's called a paradox, even though it's not a paradox. From full determinacy, you can actually prove that this is not possible, that no such a composition exists. So under full determinacy, there is no such weird thing. And actually, the reason you can prove this is because you can prove that every subset of R3, of three-dimensional space, has volume. This is a measure which you can use to measure all sets of subset of R3. And therefore, if you have a measure, you couldn't just change, like break something and then create more measure out of nothing. It has to be preserved. So full determinant seems to have nicer consequences there. Here's another one. Using the axiom of choice, you can show that the groups, or the additive groups of the reals and the additive groups of the vectors in R2 in the plane are isomorphic. So there is a map from the reals to R2 that preserves addition. And addition in the reals is addition in R2 is as vectors. These two groups are isomorphic. This is a very strange map. It's very hard to model. Full determinacy shows that it's not possible. So there is no such map. These two things are actually different groups. They are non-isomorphic groups. They are different. Actually, it proves something more interesting than that. It shows that all group isomorphisms between complete metric groups are actually homeomorphisms. So they are topological isomorphisms. Topologically, R and R squared are definitely very different. That's why you couldn't get an isomorphism between the two. Okay, so in terms of consequences, full determinant seems quite nice. And axiom of choice just brings these weird things. So am I trying to look for an alternative to the axiom of choice? Is that what I'm hinting at here? What do you guys think? No, that's not what I want to do. And I don't think many people are trying that. So the axiom of choice is very well accepted in all of mathematics, and there are many results in mathematics that use it. And actually there are, in set theory actually, where this is all developed, axiom of choice is super important. And like majority of theory of cardinals use axiom of choice quite a bit. So nobody is trying to get rid of the axiom of choice here. Full determinacy, on the other hand, has no claim here, because if you think about it, I mean, every infinite game has a winning strategy. I mean, it's nice, but I don't know if you have a clear intuition of why that should be true. That every infinite game has a winning strategy. I'll give you some of that intuition in a little bit. So what are the things we care about? So for instance, can we get a partial version of determinacy that is true? So that could be useful, because determinacy is pretty useful. Full determinacy might not be true, but maybe some partial versions are, and that's going to be the case. So there is a recent study, there are studies on set theory of how much determinacy can one actually prove in CFC, which one can prove some amount of determinacy, and can we rescue some of its nice consequences. So these are interesting questions despite the fact that full determinacy might be too much to assume. So let's take a look at this. So before going into those results, let me just give you an idea of how determinacy works in finite games before we go to infinite games. So when I talk about finite games, I'm not talking about the game of soccer or basketball. I'm talking about games like this: chess, checkers, Go, Reversi, Connect 4, Tic-Tac-Toe, etc., etc., etc. That's the kind of games I'm thinking. So these games, if you want to formalize what they mean, they are games between two players that play one after the other. At each point, the player has only finitely many possible moves. In the case of finite games, in the case of infinite games, you want to have infinite possible moves. In the case of finite games, each game must end after finitely many moves. You cannot go forever. And the outcome of the games is fully determined by the moves that the players make. There is no randomness involved. There is nothing else. There is nothing coming from the outside that's gonna affect the winner of the game. It's 100% determined on what the moves are. Okay, so like in those games, chess and checkers, etc. So it's an old theorem that says that in any such game, one of the two players has a non-losing strategy. So what's a strategy here? So by a strategy, I mean a function that tells you what to move next, given as an input what is being moved so far. Okay, so that's a strategy. A strategy is a function that is always the same, that it tells you that you input what's been done so far in the game, and it's going to tell you the next move. So that's what I mean by a strategy, a function like that. By non-losing strategy, just being picky, because in some games there are ties, one wins or there's a tie. If there are no ties, then you have a nicer game that says one of the two players has a winning strategy. Okay, so that's the thing. Always, either the first player or the second player must have a winning strategy. If there are ties, then all you can guarantee is that you have a strategy that is going to allow you not to lose, at least for one of the two players. I mean, they cannot both have winning strategies because, well, one of them has to win. By the way, what is a winning strategy? So a strategy is a function that tells you what to move next. A strategy is said to be winning if it doesn't matter what the other player does. If you follow the strategy, you are guaranteed to win. Okay, so a winning strategy is a strategy that always wins, doesn't matter what the other guy does. So for instance, you couldn't have both players have winning strategy, because if they all follow the strategy, well, one of them is going to win. So one of the two strategies didn't work. So a winning strategy must work every single time. Okay, so almost one of them can have a winning strategy, and this old theorem says that always at least one of the two guys has a winning strategy. Okay, so let's give a proof, or a sketch of a proof of why this is the case. So first, we have to make this observation, and that is every finite game can be viewed as a tree. What do I mean by a tree? Like that. So here is tic-tac-toe, and there is chess. So here in the game, so you start with the starting position, and then for the next move, you have, I guess, 9 possible places where you can place it. And I guess all these 9 moves are equivalent to one of these 3, either a center, a side, or a corner. And then after that, the opponent, now circle, has a bunch of possibilities where to move next, and it depends on each case, more possibilities. And then after that, more possibilities for the first player, and then for the second player, and then this is a tree that is branching down, and at every step there are only finitely many possibilities, and it ends after finitely much. Right? That's because of a finite game. And the same with chess. I guess you start with the starting position. That's not the starting position. You start there, and then there are all the possible moves. There are, I don't know how many there are, a few dozens, and then from there you have a few more possible moves, and then more possible moves, and then more possible moves. It gets pretty big. The size of the tree for chess is pretty huge. I don't know, 10 to the 80 or around up there, pretty huge. Yeah, around in the scale of the number of atoms that are in the universe, that will be the size of the tree for chess. It's still a finite tree. Okay, so every game can be represented as a finite tree, so now we can think of a tree. And essentially what you're doing in the tree, every time you make a move, you just go down the tree, and then the other one goes down the tree. You go down the tree, your opponent goes down the tree, and then that eventually ends, and when you end, you look at the position, and then you say, oh, who won? So at the end of the tree, it's called a node, when it, a leaf, when the tree ends. At each leaf, one of the two players is going to win, depending on the tree. Very well, so here is an example, a simple example of a tree like that. So here there are two players, red and blue. And the way, so you start up here, and then so player red plays first, player one is player red. Then player blue is going to play next, one of those four, and then player red is going to play. And then it's going to end the game when you reach one of these squares. And they are painted like this, like the red square means that red wins, and the blue squares mean that blue wins. So, for instance, suppose, so you start up here. Now, let's say player red plays up here, and now it's blue's turn. Blue, if he plays to the right, he's going to lose, so he's going to play to the left. Now it's red turn, and red comes up here. And then blue comes up here, and blue wins. Okay? So there can be many possibilities for this game. You play until you end, and then that's it. Okay, so now we want to figure out the winning strategy for this game. I recommend you guys pause the video right now and try to figure out the winning strategy before we move to the next one. So winning strategies, how should you play this game to make sure you win? And who's gonna win, red or blue? Okay. Okay, so if you pause the video, welcome back. Now let's go and try to see a solution. So okay, so let's look at this guy. So right here, if you ever get to play here, if you reach to this point, it's blue's turn after that, and blue is gonna win because blue is gonna play here. So if you reach here, this is blue won already because blue has, for sure, has this move. If you reach here, the same thing. Blue is going to win from there because he can play here. From here, though, blue cannot win because both options, both of his moves are red. So red is going to win here. And if you get up here, then blue can win again here. Now we can look at the next level. And here, blue has the option to win. Well, red has no option because whatever red plays, she's going to lose right here because they're both. So red here now here has an option. So red can play here. If this is red's turn. So red, this is a red node. Blue here has no option. Both are red, both are blue. So red here has no option, both are blue. And red here just plays here and wins. Yeah? So you have to see, like in this case, of these moves is red's turn. If she has the option to play to a red node, she wins. If she has no option to play to a red node, she loses. And now in blue's case, you have to look at whether it has the option to play to a blue node, like in this one and this one. So blue wins, and then we end up with blue winning. Okay. So and how is that blue wins? Well, you have to stay within blue. So red has no option but to move within blue, either here or here. Now blue turn has the option to stay in blue. Now red has no option but to move to blue, and now blue has the option to move to blue. So then you can do this with any tree, same thing. You start painting all the nodes from the bottom up. You're gonna end up with the root being either blue or red, and that's the winning. That's the guy who's gonna win, and just follow the strategy. Okay, so we have that in all finite games, one of the two players has a winning strategy. Let's now see what happens with infinite games. This is where things get a bit more interesting. Okay, so we're going to start with the case of what is called closed games. Here is an example. Imagine you have an infinite chessboard, like the one right there, infinite chessboard, in all directions, and you have a white king against 4 black knights. And the question is, can the white king escape forever? So the four black knights are going to be trying to checkmate the king, and the king can move around, and eventually there is a strategy that is going to get the four knights to surround the king, or the king will be able to escape forever, which is the case. Okay, I'm not gonna think of the particular case. You can think about that one. I made it up, so it's not that easy to look at, though it's quite interesting. So, more generally, a closed game is played on an infinite tree. So remember, we had the finite trees, where every finite game could be seen as a finite tree. Now we're moving to infinite trees. So that means they can be infinitely branching. So in each move you have infinitely many choices, and the length is not finite. They can keep on going and keep on going, infinitely many steps. And a closed game played on is a tree. It's not the full binary tree, or it's not the full infinite tree. The tree here in this picture is only the part that is colored, only the part that is either blue or red, and then it ends. So the tree might have like end nodes, like it might stop there, and it's there, it might stop there, or at some positions it might keep on going forever, and you keep on playing. So the rule is that if the game goes forever, then player 1 wins. If you ever reach an end node and you cannot move anymore, then player 2 wins. Okay, so such games are called closed games, because actually there is a topological reason where there's a closed set showing up here. And then the example with the knights, the knight and the 4 kings, the king and the 4 knights, is such an example. In the original paper, Gale and Stewart showed that in every closed games, one of the 2 players has a winning strategy. The proof is not that difficult, and I encourage you to pause and read this and try to figure it out if this makes sense, and you can come up with a proof out of that. It's quite fun. It's a nice proof. Okay, so closed games, one of the 2 players has a winning strategy. So the theorem about finite games can be extended to closed games. What's the general setting? The general setting is like this. So now we still have an infinite tree. And again, it's infinitely branching. So assume that first move, we label the first move 0, 1, 2, 3. There are infinitely many possibilities, one for each natural number. And then for the second move, it's again infinitely branching. So forth. So again, you play a number. And so on and so forth. So every time you have infinitely branching, you go infinitely deep. And so this set n to the n is what we call the space of all the infinite sequences of natural numbers. Okay, so there are functions from the natural numbers to the natural numbers. So in other words, sequences of natural numbers. And we start playing by fixing a subset of the set of sequences of natural numbers. Okay, which we denote up here. If you notice that if you go down the path from some tree, like we do 1, 2, 3, 5, I guess 17, and then you just keep on going down the path, choosing number. At the end, we're going to end up with a sequence of natural numbers. And then, so each point in here, each point represents a sequence of natural numbers at the end of the path of a tree. So, okay, when they play, we know players play natural numbers alternatively. So they are going down the tree. Essentially, player 1 chooses the first number, which might be 1 here. Then player 2 chooses the second number and 1, and player 1 again a number, and so on. And they keep on going down the tree like this. And then at the end of times, after infinitely many steps, we end up with an infinite sequence of natural numbers. Okay, we have the sequence. And now we ask, is the sequence in the set A that we started with? If it is, if the sequence is in the set A that we started with, we say that player 1 wins. If it's not, we say that player 2 wins. Okay, so that's the game. We fix A ahead of time, And then player 1 is going to try to get inside A, player 2 is going to try to get outside A. And each different set A of sequences is going to give us essentially a different game. Okay, so the particular game you're playing depends on this set, because this set is telling you which are the winning positions. Okay, so player 1 wants to stay inside A, player 2 outside the set. So in this case, essentially the red player 1 is the red one. The red things here represent the set A, so player 1 is trying to fall inside one of these red points. Player 2, which is blue, is trying to fall inside one of these blue points. What is a strategy? A strategy is a function from the set of finite strings of natural numbers to the natural numbers. And essentially it's because, remember, a strategy is a function that tells you what to play next, given what has been played so far. What has been played so far is a finite sequence of natural numbers. It's a string of natural numbers, right? Because so far you only play finitely much of these three. So the function tells you what to play next. Given what's been played so far, what do you play next? And then, okay, so that's the same thing again. And then we say that a strategy is a winning strategy for player 1 if it doesn't matter what player 2 plays, the strategy always wins. So formally, this is said as for every n1, n3, and n5, look, this is essentially what player 2 plays, n1, n3, n5. So for all possible moves by player 2, if we consider the sequence where player 1 is following the strategy, so s of n, nothing, player 2 plays n1, player 1 follows the strategy, player 3 plays n3, now player 1 follows the strategy now with the inputs n1 and n2. And if so long as player 1 follows the strategy, the sequence that you get at the end belongs to the set A, meaning that player 1 wins. And the same for player 2. So S is a winning strategy for player 2 if for all n0, n0, n2, n4, so on and so forth. If player 2 follows the strategy, the sequence that you get does not belong to A, and therefore player 2 wins. Okay, so that's a strategy, it's a function like that. We say that a set of sequences is determined if this corresponding game, in this corresponding game, one of the two players has a winning strategy. Okay, so determine means that. So each set, remember, each set of sequence determines a game, and the set is determined if either player 1 or player 2 have a winning strategy to win the game. So the statement of full determinacy we mentioned before says exactly this. All subsets, all sets of sequences are determined. And what's going to happen, actually using choice from the things we saw so far, is that some sets of sequences are determined. Like for instance the closed sets. We proved that, Gail Stewart proved that if A is a closed subset of n to the n, then it is determined. And within choice you can show that some other sets of sequences are not determined, and neither of the two players has a winning strategy. What can we say about that? So here is, let me mention just the main results in this respect. So okay, so we said full determinacy is a statement that says all infinite games are determined, and that one is false if you assume choice. So okay, that's not that good. Contradicts the axiom of choice. Borel determinacy is a statement that says that all Borel games are determined. Okay, so if your set is A is Borel, then the game that it corresponds to this is determined. The Borel sets, for the ones of you who don't know, are built out of closed sets by using countable unions and countable intersections. So anything you can build by taking countable unions and countable intersections and countable unions again and countable intersections again, starting from a closed set, and I guess you can take complements too, is what it's a Borel set. Okay, so it's a pretty large collection of sets. Used quite a bit in measure theory, and in regular math, like the great majority of sets that are ever used are Borel in analysis, in measure theory. You rarely go beyond Borel sets. Sometimes you go, mostly to see examples of weird things. But this, like, a very large majority of sets that you can construct are Borel, and a determinacy for Borel sets is actually true. You can prove it just with the axioms of ZFC, and you only need, I guess, countable choice. So this is a result proved by Martin, very big result, and very important because it means that determinacy is actually true for infinite determinacies for a lot of games. So a lot of infinite games are determined so long as they are Borel. And then here's another interesting result. This is a bit more technical, what L of R means. L of R means the class of all constructible sets over the real. So everything you can build in a constructive way. And there is a very formal definition of what that means, which I don't want to get into it. But essentially, it's everything you can build without using choice. So sets that you can just build by, I don't know, defining things, and then using the subset axiom, and then using ordinals and transforming recursion, and using any real that you want to use. It's a parameter. So it's everything you can construct essentially in set theory. And it's actually very general. Anything you think of that I can construct, it's going to belong there. But if you need to use the axiom of choice at some point and say, oh, just give me a choice function for this, that's not constructible. Okay? So all the sets that are constructible, this is a much larger class than Borel. The statement that says that all of those are determines may be true. So if you take some assumptions that are a bit beyond ZFC, but that most set theorists believe should be true, whatever that means, then you can show this is actually true. Right, so the assumptions go beyond CFC, so it's not obvious what that means that is true. But yeah, it's usually believed that yes, these guys are true. So essentially every game that you can construct will be determined. One of the players can have a winning strategy, while there are cases when you can use choice to build games which don't have winning strategies. And then you get some very nice consequences for these results. You get, for instance, that all constructible sets of the space of Rn, n-dimensional vector space, are measurable. You can assign a volume to these things, and you don't get weird things so long as the sets that you're dealing with are constructible. So if you're proof you're building the sets, fine, you're not going to find any weird things. The continuum hypothesis holds for constructible subsets of R. So if you take a subset of R, it's going to be either countable or have the size of reals. So you don't have intermediate things. You don't have subsets of R whose size is in between the natural numbers and the real if you restrict yourself to constructible subset of the reals. You also don't get no group isomorphism between these two spaces, like the line and the plane, which is constructible. So these are essentially, you can prove these things depending on what your assumptions are, what you let constructible be. But these is things you can somewhat prove. So you can use these things. So even though full determinacy, we cannot adopt that as an axiom if you want to assume choice, we still get pretty nice results out of it, all of these guys. And by the way, let me just mention, sometimes it is used as an axiom. Like people say, what happens in the case when you have full determinacy and you only have countable choice and not the full axiom of choice? And yeah, there is some work done there, and it's some interesting space that you get, some interesting world, universe. See you guys later.